Today we are diving into a really important concept in astronomy and astrophysics called a spectral signal to noise ratio or SNR in a brief. So, what is a spectral SNR and why does it matter to the analysis of a spectra of a star or any galaxy? So, whenever we observe light from a star or galaxy, or any astronomical object, so light spreads into the spectrum and basically it separates into different wavelengths or colors, and this spectrum contains a lot of information about the object temperature, composition, velocity and other parameters. But here is a catch: our observations are never perfect, so there is always noise, random fluctuations caused by the detectors, the atmosphere, or even cosmic ray. So, signal on the other hand is the actual useful information like the light from the galaxy we are studying. So, signal to noise ratio or SNR is a measure of how strong the actual signal is compared to your noise present in the data. So a higher SNR means much cleaner data with finer features in the spectrum like emission and absorption lines. A low SNR means data is messy and harder to interpret. So here SNR is defined as the signal to noise ratio, okay, or flux from the object divided by flux error. So in astronomy, we often aim to obtain a SNR value of 3, 10 or even higher, depends upon your scientific goal and result, and it can depend on what you are trying to measure, and because some task needs much higher SNR of the spectral lines. So throughout this video, we'll explore how to plot your SNR uh, from a actual galaxy fits a spectra obtained from Sloan Digital Sky Survey data, in which there is a BOSS spectrograph, right? So these things will be doing with actual Python coding and real spectra of a galaxy. So let's get into it. So our step 0 is to download our galaxy fits a spectral file from Sloan Digital Sky Survey BOSS spectrograph data. So I'm not going to download these fits spectra again and again. So for that you can watch this given video on the screen, or alternatively you can click on the top right of the video, and you will be able to access the same video, and you will be able to download the data. And I will also provide the link to this video in the description, from where you can uh, download your data file. Now we will be doing step number 1, in which we will import our necessary and required library. So I will import Numpy NP, which takes care of your numerical computations, number and arrays. Then I will import Matplotlib dot pyplot as plt. So this will take care of your data plotting and visualization. And then finally I will import Astropy. So from astropy.io import fit. So this will take care of your fit file handling, right? Now come to a step 2, right? So which is our reading our feeds spectral file. Okay, so let me check which spectra file I have. So type here ls star feeds. So it will basically you give the file name which have extension dot feeds. So here I have a spectra dot feeds. So let me copy this name and remove this command, and then I will uh, read my feeds file. Okay, so for that type here a spectra, right, a spectra file. Okay, so type here command feeds dot open function, right, and give your file name in a string, right, spectra dot feeds. So basically this will read feeds file. Okay, now we have read the feeds file. So now what I will do, I will extract the information like where my spectra is and in which header data unit. So file information. Okay, so for that type here a spectra file variable and give attribute dot info and function. Now run it. So here you can see that you have 4 or 5 uh, header data units. So primary, quad, and aspect object. So my spectra is in the quad SDU, which type is printable SDU, and it has 26 cards and this much of rows and 8 columns, and data format is this. Okay, so our objective is to extract this SDU. Okay, so for that type here data equal to a spectral file. Okay, and then give here 1 or give this SDU name. Okay, so and dot data attribute. Okay, so this will read your data. So yeah, so this is how the data looks like. You can see you have a flux column, you have log wavelength, right, you have invariance, mask, and you have skylines and some models. Okay, so now our job is to extract this flux column, wavelength column, and inverse variance, which is used to find the error in the flux. So let's extract one by one this column. So for that I will first extract my flux column. So give here variable name called flux, and then go to your data table, and then give a square bracket and extract this flux column. Okay, so just you can paste it here, and if you see the flux variable, so it will return this array, right? So in the same fashion, you can also like extract the wavelength, right? So quote here lambda variable, and then you can give a data and just copy this keyword log lamb and put it here, right? So you can see this is wavelength is in log, so give here 10 raised to, so that this comes in the format of I mean it comes in the linear format. right? After that, you can extract ivar, I mean first variance. So basically, this is 1 by sigma square, right? So what I will do, I will take uh, as a data and then give, right? So now this will be used to find error in flux. Okay, so for that, type here say flux error, right? Flux error equal to, okay, so first convert into your uh, okay, the variance sigma square, right? So this is what my sigma square, and then take its a square root. Okay, so basically it will give your flux error, right? So if you see your flux error, so this is how, what is the mistake here? ivar is not defined. Mm, see the keyword, right? So yeah, let me check it once again. Yeah, there is a capital IUCAA, so make it a small. Now I think it's fine. Okay, so we got here all the required flux wavelength on the linear scale from log scale, and then you got your flux error values, right? Now a step 4 is to calculate your SNR, and the formula is given as flux divided by flux error. Okay, so type here SNR. Okay, SNR equal to, you can give flux divided by flux error, right? So this will give a number, right? So you can see how much SNR is, right? And then you can plot this spectra, right? So first of all, what I will do, I will just plot a simple flux versus wavelength of this spectra. So add a cell here, and then you can type here plt dot figure, right? And then type here plt dot plot, or just make it a step plot, and you can give lambda and flux, right? And run it. So here you can see, here is your spectra, right? And here some emission lines have been given with the highest peak values, right? So yeah, so now what we will do, we have to plot the same spectral plot, but this time your y should be SNR, okay, not the flux. So let me give a title here first, plt dot x level as the wavelength, right? Wavelength, and then plt dot y level as a flux, right? Now I'm going to plot this SNR plot. Okay, so for that, give here plt dot figure, right? And then you can type command here plt dot plot. You can give your lambda wavelength, and then you can give the SNR, right? And then you can also give your title, sorry, x level. So same, it's a wavelength, and this time your y level is going to be signal to noise ratio, right? just code here SNR and make it as a string and then do it here plt dot. So this is what is mistake here. X label there should be, yeah, A should be after L. Okay, one more mistake is there. Y label. Yeah. So here you can see that this time your y-axis is different on a scaling. Okay, it is going from 0 to some 40, right? So this is how my SNR of the spectra looks like. You can see some lines have SNR 10, 15, and some have 40. Okay, so you can mark a say label here plt dot ax each line, and you can see like y equal to 3, and this is, yeah. So you can give color equal to say red and plot it. So this is my line of SNR 3, right? You can give a label here also if you want. Label equal to SNR 3 and SNR 3 and string, and here you can give label as a SNR data, right? And then mark here plt dot legend, right? So for completeness you can see this is my SNR data and this is for SNR 3. You can also check for 10. So 10 is like very good SNR and 3 is like minimum. You can proceed with 3 SNR for further spectral calculations and finding some parameters using flux. Okay, so this is 10, this is 3, and you can also go beyond that to see like which line is beyond which SNR. And so let me review the code once again. So from starting, so I have data from SDSS telescope BOSS spectrograph. After that, I have imported Numpy, Matplotlib, and Astropy library to read and visualize the data. And then in step 2, I have read the spectral feeds file, and then I have got some information about the feeds file. So we found that in our second SDU co-add there is our spectra, right? And after that we have extracted the flux value, flux error and wavelength from the co-add SDU, and after that I have extracted this flux wavelength on the linear scale from log scale, and then I have extracted the invariance column which is used to compute your flux by taking the square root of the inverse, right? And then I simply then find out the SNR from this formula, flux divided by flux error, and then I have simply plotted a spectral plot wavelength versus flux, and finally I have visualized our SNR plot for your each wavelength or each your pixel. This is how my final plot will look like. So I hope you got the idea that how to plot and visualize your spectral SNR for each pixel in wavelength space. So you may create this plot with your own, and if still you feel any difficulty, then you can let me in the comment section I will be happy to help you. So, thank you.